So take a look at these limits. We've seen several of these before, right? We've seen the top one, and we've seen the two in the middle. And we had ways to do them, right? The top one, we do this thing where we divide the top and bottom by x, right? And this left-hand one, we did this kind of weird thing where we rationalized the numerator. And sine x over x, this was the one, we had to use this kind of trig property that the sine of x is less than x if x is small, and then we used the squeeze theorem. And boy, this bottom one, I don't know, we haven't even looked at that guy yet. So there are ways to do them, but there are better ways. And what I want to do first, I want to look at all of these, and I want to think about what they all have in common, right? If we try to just do the direct approach, right? Missed some parentheses. There we go. We try to just do the direct approach and substitute the limit number, right? This one becomes 0 over 0. This one, square root of 4 minus 2 is 0, and 4 minus 4 is 0. Up here, I mean, if you think in terms of taking the limit of the top and the bottom separately, this becomes infinity over infinity. And down here, the log of 1 is 0, and 1 minus 1 is 0. So you see a trend here, right? A lot of these are coming out to 0 over 0. And then the top one, sometimes we get this infinity over infinity. And this kind of limit, a limit that ends up this way, has a special name. It's called an indeterminate form. And it turns out there's a really slick rule that we can use to evaluate these limits much more simply than all of the kind of hacks that we've had to use so far. And to kind of intuitively see what's coming up here, look at this top limit, the infinity one. Remember, the idea here was the function in the numerator is a line, and it's moving, it's changing at a fixed rate of change. And this function down here in the denominator is a line, and it's moving at a fixed rate of change. So even though both functions are going to infinity, the rates at which they're doing it have this relationship, right? And that relationship ends up being the limit. Okay, I want you to think about what I said there, right? I kept talking about comparing, instead of comparing the functions, comparing the rate of change of the function. All right, well, we have a way to talk about rate of change now, right? The rate of change of a function is its derivative. So how about this? How about, instead of comparing the functions themselves, how about if we compare their rates of change? Well, if I do that, what's the rate of change of the numerator? Well, the derivative of 3x plus 2 is 3. And what's the rate of change of the denominator? Well, its derivative is 2, and that limit, since there's no variables in there, the limit of a constant is just the constant. And that was the same number we got by the methods we developed for dealing with the limit of a rational expression. Right? So this is going to be our rule. All right, so let's take a little deeper here. First, I just have a definition. Right? I just want to be clear what I mean when I talk about an indeterminate form. If we have a limit of this form, right, it's a limit of the ratio or the quotient of two functions, and either both functions go to 0 or both functions go to plus or minus infinity, then the limit is what's called an indeterminate form. And they come in two types. There's a 0 over 0 type and the infinity over infinity type. All right, and as we saw on the last slide, all four of these limits that I'm talking about here fit into one of these two categories. Okay, so what's our rule? How do we handle these? All right, it's got a name. It's called L'Hopital's rule. L'Hopital's it's a guy's name. He's a French mathematician. I mean, what his rule says is if we have two functions, right, f and g, and those functions are differentiable, and the limit as x approaches a of both functions is 0, or the limit is plus or minus infinity. In other words, this limit here is one of these indeterminate forms. Then, to find the limit, instead of looking at this original limit, I can just differentiate both functions and look at that limit instead. Okay, you notice I kind of skipped it, but we do have this one extra caveat up here. G prime of x can't be 0 in the neighborhood of a, right? Which is kind of makes sense, right? G prime of x is what ends up being in the denominator, and we don't want the fraction of the denominator of a fraction to be 0, because that messes everything up. So we do have that one extra little caveat. Okay, so let's see how this works, right? And I want to refer back to another one, right? We already know what this is. We've seen this one. It's 1. Okay, so let's see how L'Hopital's rule works. See if we can kind of confirm that result. First, when you're doing this, first thing you need to do is confirm that this is, in fact, an indeterminate form. Right, and we did see that earlier. The limit as x approaches 0 of the sine of x is 0. The limit as x approaches 0 of x is 0. So, yes, this is an indeterminate form. So what I'm going to do to apply L'Hopital's rule is I'm just going to take the derivative of the top and the derivative of the bottom. And this limit becomes the limit as x approaches 0. See, the derivative of the sine of x is the cosine of x, and the derivative of x is 1. And you see what happened there, right? That variable that was that function, that variable that was dropping a 0 into the denominator just went away. Now I can do this just by substitution. This is the cosine of 0 divided by 1. The cosine of 0 is 1. 1 divided by 1 is 1. And that's it. There's my answer, right? 2 very short, simple little calculus steps. Much easier, right, than trying to invoke squeeze theorem and all sorts of other geometric arguments. Okay, so that's the basic idea. Right now we've got it down. In the next lecture, we're going to look at a bunch of examples. Right, look at a bunch of examples, see how this theorem gets applied.